Can you hear me now? Okay. I see. Can you hear me now? I'm so sorry. Okay, I've been yelling and screaming. Okay, you can. That's a good start. All right, I apologize. I've been asking you guys to do things. Okay, so as you see, we're having device issues, major device. I'm on the tablet that is what I use to do your whiteboard. But I normally have two devices going. Normally, I'm on a computer zooming to you, and then I use the tablet for whiteboard. So, my computer uh, is a real problem right now. We're gonna okay, wait. So let me start. So I apologize in advance. This is going to be not the way I want it today, but here we are. Um, let me start. It sounds like you can hear me. Wait, I'm going to look in the chat. All right, let me look in the chat. You can't hear you. Okay. No, yes, you couldn't hear me. That's my now. I apologize. But now you can hear me. It looks like. Okay. Thank you, all of you. Okay. So let me back up. And we are recording for what it's worth. I mean, I don't know where this recording is going because it's not going to my computer. I mean, it's going to the cloud, and hopefully I will be able to find it when we're all done. So whatever we get done today, which I hope is a lot, even if it's all funky and weird, we'll still post all the notes for sure, and we definitely will take notes. Anyway, I'm apologizing because I'm having major device issues right now. Like literally, I don't have my computer. That's the it's in the shop, and they lent me like a Kindle Fire, which is not really equipped for this situation. But I'm going to try to make it work anyway. So I'm going to start again. So if you couldn't hear before, that was my fault, not yours. Um, right now, since I'm on a tablet, I'm just looking at the chat. I can't see you yet, but let me say hello, Jamie. Hello, Mira. Hello. Oh, okay. I'm going to say this in advance too. I'm still mispronouncing some names. Please correct me in the chat. Hello, Josh. Josh isn't the name that I'm mispronouncing. I'm just saying. Hello, Antigone. Hello, Takarub. Hello, Layatule. Let's see, I'm Layatulai. Um, hello, Yichan.
Hello,
Hello, Michael.
Professor.
Oh yeah, hello. Thank you. Oh, now I can hear you too. That's good. That's helpful. Thank you. Anything we could do to overdo it today would be good because I'm like in a black hole here. Okay, but thank you. I'm not sure I know who that was, but thank you. Or maybe that
That
was.
was live to live, Professor.
Oh, thank you. Okay, and I'm saying your name sort of okay, sort of, or not really yet. Am I sort of saying your name okay? Say your name.
Yeah,
Yeah. Okay. Okay. Great. Okay. Thank you so much. Thank you. Okay. Okay. And hello, Montserrat. Who um who I also hope I'm saying your name right. I've had well, it doesn't matter. Okay, I'll keep going. Hello. Now why am I doing this wrong? She even told me. I know you even told me last time. I want to say Amelie, but that's not right. It's not Amelie. It's you'll have to tell me again. I'm so sorry. But we'll get this eventually. But hello. Oh, see, I can't say your last name. Hello, Ms. Chikoye. Anyway, hello, Alirat. And hello, Antigone. I guess I said that. Hello, Jamie. I guess hello, Mira. Hi, Montserrat. Hello, Michael. Okay. So hello, all of you. Now I'm going to go back. Let me see who I can see. Uh, Okay, so I can see you guys now, sort of. Thank you for those of you who are showing avatars or avatars, whatever. Oh, and there's thank you. Hello, Layatule. Good to see you. Thank you. And also I should say to all of you, by the way, thank you for doing that. And that counted, by the way. Those of you who caught the 5 seconds of Layatule, he can submit for points for that. I'm just saying, 5 seconds is great. Also, all of you, I should make clear it's very and there's Antigone. There she is. All right, thank you. I appreciate it. Especially today, that helps me a lot because today we're like on a shoestring here, and we are going to get things done. In fact, we have more to do than I'm going to get to. But anyway, also just want to remind you all, or maybe I never said this. It is very considerate of you that you're on mute. Like I definitely understand being on mute, like especially if you have a dog in the back. Oh, and hello, Mira. Good to see you. Excellent. Good to see you. Thank you. Even if for 5 minutes. Thank you. And Antigone. Okay. If you and there's Madonna. Thank you. Good. This honestly, you don't even. This is like group therapy for me now. Thank you. Okay. And Sebastian. Hello. Good to see. Good to read you. Just the thing about the muting, it is a good idea to be on mute if you have like, and I'm not joking, if you have a dog in the background, which I frequently do, or like a child, or just like construction noise, then yeah, the mute is good. But other than that, like if it's silent where you are, you can stay off mute if it helps you feel more comfortable to like interrupt me or to say things. I'm all for it. Like you really, I should be the one that should be on mute. Really, you guys should not be on mute. But I do, yes, of course, if there's background noises, then yes. Okay, anyway, just saying. Okay, I'm gonna try for 1 second. I'm gonna try one more time to turn on a different device so that I can do this properly. I'm just not I don't think it's gonna work. It hasn't all week. I've had my computer in the shop, and all week this has been preposterous. But I'm gonna just try one time. Bear with me for a second. If I can get my face on a different device and then use the board on this, that would be better if I can. Bear with me for a sec. But I know we have a lot to talk about. Well, I think we have a lot to talk about. Oh, this is interesting. I might end up joining as a student rather than teacher, but maybe that's okay. Let's see. Maybe I'll have more sympathy and be a better human being if I join as a student. Interesting. So I'm in my own waiting room. Okay. Okay. I knew what that waiting room looked like. Very nice. Okay. Oh, no, maybe this is good. Maybe I'm seeing what it's like to be you. Maybe that's good for everybody. Okay, hang on. So, okay, I'm in two places at once. That's a little odd, but okay. Wait. Here's what, bear with me for one more second. We'll see if this works.
Recording in progress.
Wait. I know why that's happening. Sorry, hold on. Just bear with me for one more second. I know that I'll make a joke while we're doing this.
Professor, you're on mute.
Thank you. Wait. Okay. Am I? So you can hear me now, but there's an echo, correct? No. All right. Wait.
I don't hear an echo.
Oh, all right. That's good. That's good. All right. But I do. So let me try one more thing. Sorry. This is so. I'm going to try to. Okay. How is this now? Can you hear me now? You can't hear me
Yes,
now.
Professor. Yes,
Oh,
we can hear.
you can. Oh,
Yes.
okay. So maybe this works now. Okay, this is so crazy. All right, sorry. All right, but if you can hear me, and we'll try one more thing. If you can hear me and you can see the notes. So can you hear me and see the notes?
Yes, Professor.
Great. She's like, yeah, Professor, what's the problem? Okay, good, fine, good. I'm glad. Then we might be in business. Okay. That's a relief. This is like, okay. we'll start. Just one quick thing, just to make fun of myself. This is so totally stupid, but just to break the ice. I have two sons. They both have gone through Zoom schooling, and it scarred them both. I'm very sympathetic to the whole thing. But the older of my two sons is like basically your age or the age of some of you. I mean, he's 19, and he introduced me a long time ago to this YouTuber. This is just totally ridiculous. I'm just telling you this for fun. There's a YouTuber called Gus Johnson, or he was Gus Johnson. He was very popular at one point, very silly. I think he's been canceled now for some reason, but none of his YouTubes are inappropriate or any. I think they're hilarious. They're not inappropriate or gross or any, or well, maybe some of them are, but not the ones I've seen. But one, and I don't know if you've ever heard of him. If you have, maybe put in the chat just so I don't feel crazy. But anyway, this guy named Gus Johnson does one YouTube, or did a long time ago, one YouTube called "How to Be a Professor," and he pretends to be a professor, and he spends like 45 minutes of his hour lecture failing at all the technology in the most awkward, embarrassing way. And it doesn't escape my attention that I'm not just a professor, I'm a physics professor. So it's pathetic. I mean, it's totally pathetic to waste your time with it. But if you ever want to check out that video, it's even more awkward and ridiculous than I am. And I think it's spot on. Anyway, that's just a recommendation of outside reading that is not required for this class. Okay. But I'm glad somebody's smiling, sort of. Okay. So I think we have the technology going now, sort of. It's weird on my end, but if it's normal on your end, good. It will be recorded, blah, blah, blah. And someone's here, I think. I think someone's here. I'm looking at chat. Okay. If you see that someone's in the waiting room, let me know, because look, again, I'm going to stop apologizing. I'm going to get to it. But what's awkward about this is I'm literally hosting from the tablet part and then trying to be a guest in the computer part. So it's very disorienting. I feel like I'm in Alice in Wonderland. But so if someone's in the waiting room, let me know. I have a feeling someone might be. But let's get to business here. First of all, you had some homework due today. Let's back up. First of all, you all did a game turn to indicate your participation or your engagement last time during class. I think every single one of you did it, I believe, and every single one of you got it back for 5 points. That's terrific. That means we're off to a good start. That was great. Just a reminder then, again, tonight, there's another one already posted. Tell me if not. Do 11:59 tonight. Same routine. Just put in one quick indication of one quick way that you participated. And as long as you do it by midnight, you get the 5 points. If you do it tomorrow, you get 4 points. If you do it the wrong way somehow, like you put it in the wrong place or something, I'll probably give you 1 point just to alert you that something needs to be fixed, but then you'll fix it and then you'll get probably the rest of the points. If you put in participation things to any of the other portals, I hope you did. I may not have seen them yet because of this whole device issue, but I will see them. And if you put something in, like, for example, if you showed video and you put in the video portal, I apologize if I haven't returned that to you yet, but it's there and you will get the points for that. And just to say, to make clear something, say you last week, like you went and stop me if you don't know what I'm talking about, or put something in the chat if you want more clarification on this. But say, because many of you do show video, and I love it. So, like all of you, like right now, Yi-chan, Josh, Madonna, Mira, Antigone, it's great, right? So, and for 5 seconds earlier, and I don't mean that sarcastically, like Laya Tule showed video. So every single one of you is eligible just to take a screenshot, right, and just post it in that portal called a game.video. And then you'll get the points for that. And that you could do anytime. If it's for today, like do it tonight, do it tomorrow. But the one catch, say you did it last week. Terrific. If you did it last week already, I still owe you points for that. The only thing I'm asking is leave that upload from last week already there. Like, don't take it down. Just add a new upload, a new attachment. And for each file that I see, you'll get the appropriate points, even if I fall behind. For every file that I see there, you'll get points. Quick note on now, that's like a minor thing, but as far as real homework is, I shouldn't say real, as far as physics is concerned, which we now have to start talking about. That becomes interesting too, because with physics, remember, if you don't get a perfect score on something, you still always, until I say otherwise, once we start going over homework in class, like we're going to do today, you can always, you are encouraged to revise your homework and upload a revision and get more points. Like until you get all the points, you're allowed and encouraged to do that. So the one catch is always leave your old version up there as well. How do you do that in Google Classroom? It's a little funky. You may have to play this again later, the recording, or talk to each other for help. I think you guys have to set up a WhatsApp, or you set up a Discord or something. I hope you did. I believe I remember that you did. If you didn't, please do for yourselves. And you can do it like right now in the chat if you want, if you didn't already. But I think you did. But so here's a little bit funky how to leave something up there and put more things, excuse me, up. What you have to do, and it's counterintuitive. Some of you know this already, of course, but if you don't already know this, you wouldn't necessarily guess it. If you want to add new attachments or get like a new grade on something, which again, I'm very, very interested in you being able to do, what you have to do is go to your assignment and hit the button that says unsubmit. It kind of sounds scary. It sounds like you're taking things down or erasing things. You're not. If you say unsubmit, what you're just saying is this is no longer my official submission. It doesn't change it doesn't erase your grade, and it doesn't erase the document or like it doesn't delete the document. It just means that's not official anymore. It's like backsies. So then you go to the option that says add another attachment or add new attachment or something. So you add your new file. Okay. And then you hit submit or turn it in, whatever that button is. So now both will be up there. And that's what you do in general. Whenever you want to improve your grade or revise something for more points, or in all of those game portals, if you every week you want to say that you showed video, and every week you want to say you used your voice, and every week you want to say you helped a colleague, then just keep doing that. Like unsubmit, reattach, unsubmit, unsubmit, reattach, submit. So please do. Again, with the game portals, I haven't gotten to them yet if you already did them. So I want you to know that. I'm going to pause for a second. Can I just get any kind of indication for you guys that that was clear? Does that make sense? Yes, thank you. Okay, thank you, Mira. Okay, thank you, Josh. Okay. And again, remember the dichotomy in physics. At any given moment in physics, things are either clear and totally boring, or they're exciting and totally confusing. So whenever it's boring, just think, well, at least it's not confusing. Okay. All right, so that's clear. Next thing on the sort of now getting to the kind of real home, like the more physical homework we have to get to now. On the homework 1A. No, let me go back. Well, yeah, no, homework 1A, UnthingyThings. That was like I mentioned, sort of informal, sort of casual, definitely worth discussing. We have to discuss. We will discuss in a moment. We're going to go over it. All of those, I hope you found all of your unthingy things, assuming you submitted it, which I think, honestly, I think every single one of you, except maybe one person, did. If you submitted that, then hopefully you saw you got some feedback on it. Not a ton, but you got, like, I hope you can tell I read what you said. It's going to inform our discussion today. Now I know where you all think about that. And I'll tell you what the purpose of it was, but it wasn't formal. You didn't need to do the 5-step problem solving method or anything like that. The only main formal thing about it is I wanted to see that you understood to hand in a separate sheet by itself, one file, not a bunch of JPEGs, but one file. And that's what overwhelmingly you all did. As long as you did that, and as long as you got feedback on it at all, as long as you correctly submitted it, then you got all points. I think it was 20 points. You got all the points, and that's as it should be for that assignment. So you should, if you think you turned it in on time but you didn't get it back, you should let me know, and we're going to discuss it. You're going to see why we had that weird assignment in a moment. But then let me just, the last thing I have to cover is homework 1B, where we really now get into the physics, right? We start really getting into the stuff that you're doing in the lab in the first week and maybe in the second week. We really have to start rolling with all of that. With homework 1B, just to be clear, I put this in the classroom. This is how I do things. With 1B, it starts straightforward, but it gets sort of hard by the end, I think. Or for some people, for me, it gets sort of hard by the end. If you got a 15, if you got 25 points on it, I hope it's clear. That's like a starter set of points. That is my way of acknowledging to you, thank you. I see your homework. Great. You submitted it correctly. You are in the class. You clearly know what's going on as far as instructions. So you've already gotten 25 out of 35 points just for being a good citizen and for being on time. That's all that you got so far because it was only just due now. So that I have not gone through yet to give feedback or anything. Anybody who got 25 points, I want to make it clear you've gotten so far 25 points. You will get more points. I guess I made it clear, but you'll get more points once I actually start going through it. And we will start going over it today. I will start helping with it today. Any of you, if you start learning things today that like make you realize, I guess I actually did that wrong or something, you can upload a revision. Don't erase your old thing, but you can upload a revision and you can put a note in there that says, when you get to this, professor, please look at my more recent thing, not my less recent thing. And I will. But I'll just also see, look how responsible this person is. They're like literally correcting as they go. Totally great. So anything you can get out of today's class, if it helps you, so we're going to start going over it, and you'll see if you were right or wrong or whatnot. But if it helps you and you want to change things, all the power to you. Okay. Also, we're still at the stage, last thing. If anybody's late with anything right now, if you still owe me something, you should still turn it in. You could still ultimately get all the credit. One of the reasons that the people that turned it all in already have gotten 25 points is as an acknowledgement. Like, of course, it's better to turn things in early rather than late. But we're still at a stage now that definitely late is definitely better than never. And the worst thing that's going to happen to the people that are late right now is they're going to start falling behind, and it's going to be more difficult for them. So that's like, so anybody else who's like killing themselves to be on time, don't worry. It all works itself out in the marketplace, sort of. But so if you still owe me something, please don't think it's not too late. Okay. Okay, that's on that. All right, now what I want to do, I want to start using my board and getting to going over the homeworks. And that's what I'm going to do like right now. I'm going to ask you first, before I move to the homeworks, I'm going to say two things. Well, one, are there any questions or any like larger things that I forgot to address last time, or any larger concerns or any questions at all before I start going over? I'm going to go over homework 1A, maybe sort of quickly, and then move back to homework 1B, which is like really where the physics is, the direct physics. But just in case, before I do that, are there any questions or concerns or larger? And again, you might have to scream if there are, because I'm not even sure I can find the chat, but are we good? Or Josh, are we good? Yeah. Okay. Thank you, Josh. All right. I'm not picking on him. But thank you. And thank you, Madonna, sort of, I think. Okay. Okay. So, yes. Thank you, Madonna. There's Madonna. Okay. So I can see the chat. All right. So I'm going to move on to homework 1A. Oh, the other thing I'm going to ask you today, one of the big things I regret from last week on my side, not on your side, is we are supposed to spend, as far as I'm concerned, we should spend a reasonable chunk of time of each of these double periods reviewing and discussing your lab experience. We did not do that last time. My experience is the first lab usually sort of goes okay. I still want to review it with you. But by the second lab, often people have some real questions and concerns, and I'm here to help with that. They're supposed to be communicating with each other, the two pieces of this course. So I'm going to say right now, I'm going to try to sort of race through homework 1A. I'm going to try to get somewhere through homework 1B. But this class ends at 5:45. At around 4:45, please feel free to give me a heads up or a shout out or something in the chat that says, can we please talk about the lab? Feel free to do that. If I start, there's 4 people in the waiting room. Okay. If I start losing, God, I don't know how long those people have been waiting but okay. All right. Anyway, but until that time, so please make a note, like at 4:45 or 5, I should really shift gears to the lab. But what I'm going to do right now is move to homework. Okay. Homework one, and you can see the, well, how come I can't see the board? Wait, you can see the board, right? Or no? Can you see the board? Can you
Yeah,
see the
we can see
white?
the.
You can. All right, thank you. I wonder why I can't though. All right, well, whatever. Okay. 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 Now I'm gonna say right now, uh, I looked at all your unthingy things. There were actually a lot of different answers just in terms of which tasks were possible and impossible. Now, this could be a very interesting discussion. If we were together live and I weren't like frenetic about other things, I could imagine a very engaging debate among us about which of those tasks were possible and impossible. And there would be a debate because a lot of you actually put different answers, which, if nothing else, shows me that this is worth talking about. I will spare us the discussion right now so that we can sort of make some progress. And I'll get, well, you can interrupt anytime. Please feel free. But I'll cut straight to the chase and tell you what I think the answers are for the 5 tasks and which ones are possible and impossible. Because yes, this is supposed to be fun and relaxing, but there is a point that this whole sheet is driving at. And the point that the sheet is driving at is the point of this class. And the real point in the end is like, what do we mean by a particle? It comes down to these 5 tasks. So bear with me, maybe take notes, or please take notes, but please stop me if anything I say seems counterintuitive or something, because this is kind of the foundation of the class. So here we go. Task number 1, remember, task number 1 was, oops, sorry, place one thing, I'm gonna even say it like this. In fact, you may even need to remind me. This is this. Sorry, actually, could you remind me? I'm not looking at the sheet. Task 1 is place one mass point at. Actually, can you remind me what is task 1? Is it one? Is it one? Is it thing 1 or thing 1 and thing 2?
It's thing 1
Thing
and
one and
thing 2.
Oh, it is. Okay, okay. Thank you. All right, that explains that. That makes more sense. Yeah. Okay, thank you. So it's, if you at is it at just read it out loud, please. Actually, the whole thing. I'm retranslating it, but read it out loud. The task 1. One of you.
Task 1, place thing 1 and thing 2 in 2 different points in space at the same point in time.
Okay, right. Thank you. Okay, thank you. Perfect. Okay, so I'm writing it this way. I'm just trying to put into more formal way exactly what you just read. Okay, so this is like 2 points of right. Thing 1 and thing 2. What do they stand for? They stand for 2 objects, 2 collections of mass. And I believe the sheet made clear. That whenever we think about thing 1 or thing 2, whenever we consider thing 1 or thing 2, or name thing 1 or thing 2, what we're referring to is a point, like at the center of thing 1 or thing 2, respectively, right? Like we're supposed to, in our mind, and this is a little bit tricky for some people, in our mind, we're holding a whole pen, let's say, or a whole calculator, or a whole wallet. But in our mind, we're picturing one dot, one pixel at the kind of center of that whole object, and regarding that center pixel as a representative of the whole thing. In our mind, we're reducing the object to a, what we might call in physics, a point mass, or a mass point. Right, so we're thinking in the world. It's sort of part of the point of this whole exercise is to get our mindset configured properly for physics before we go any further. In physics, we think of the macroscopic world as a big coordinate grid, a big grid with I don't know how many axes, maybe 1 axis of time and maybe 3 axes of space, or sometimes when we're being simpler, maybe one axis of time and one axis of space or something like that. But we're thinking of the world as a big grid with lots of points in it, points that can be described by coordinates, a time coordinate and some number of space coordinates. And then we think of objects as points that fit in this grid, right? So we have points of, remember, all of physics is stuff in space and time. That's it. That's all there is to physics, stuff in space and time. Hence, like the SI units of MKS, kilograms, meters, and seconds. That's the whole world to us, right? And this whole world in our mind, when we're trying to analyze and measure it, is reduced to pixels or points. So task one, I'm just slightly rephrasing in that way, as it's asking us to place two mass points or two thingy points at two space points at one time point, right? I'm not, hopefully you see, I'm not changing the idea of what task one, I'm just like rephrasing it in a manner that might make it consistent with the other tasks. Also, this is an indication when you guys do your homework and you're supposed to do step 2, WIQ. This is an example of what I mean. Like, you write the question, but you kind of put it in your own words so that so it makes sense to you or to the reader. Anyway, so here's task 1. So, but you don't recopy the original question, right? You rewrite it. So anyway, here's the question. Can I place two mass points at two space points at one time point? Now, I think most people got the same answer for this as I got. To cut to the chase, I think the answer is almost, oh yes, most certainly you can. Like, if my 2 points, if my 2 things are a coffee pod and a stylus, like, I can go like this. And that is task 1. I have 2 mass points at 2 space points at one time point right now. And even if I'm like spazzy, right, as long as I hold still long enough, there's at least one point in there somewhere in time where I have 2 points of stuff at 2 points of space at one point in time. Now, so I would say, unless there's questions, I think that one's possible, and I think most of you said it was possible as well. Almost, I think maybe even all of you did. But then we get to task 2. Oh, I shouldn't say and we get to task 2. Task 2 was place 2 mass points. Now, I believe, you correct me if I'm wrong on this, but I believe I'm pretty sure about this. I think I know what this one was. Place 2 mass points at one space point at 2 time points. Now, again, if you look at the task on your sheet, it might have been phrased slightly differently. It might have been phrased with the words in a slightly different order. But I think, and it's an awkward one, this one. If I remember it correctly, it's awkward. It's not the kind of thing you go around saying. But if you break it down in your mind, it makes sense. It's asking you to have 2 mass points, occupy one space point, but at 2 different time points. So can I do that? I think the answer is yes. I think the answer is yes. I think I would have to do something different from what I did in task 1, but I think I can do it. I can go like this, right? And then, right? I mean, or something like, right? And then, right? It's 2 different objects. They're occupying one space point. They're sharing a space point, but they're using the luxury of time in order to do that. They're in the same place, but at 2 different times. The fact that time flows or something allows that to happen. In other words, I'm saying, and I'm trying to talk quick now just to catch up with myself, but not to prevent interruptions. I think this one is possible as well. I think some of you disagreed. So you are welcome now. You're welcome in the chat. I'm not trying to steamroll you. Some of you disagreed with this. I'm going to conjecture that maybe some of you disagree with it because you found the wording awkward or hard to like decipher. And maybe for some of you, if you're with me right now that you see what I mean by the wording, maybe now you agree. Fine, great. But if you still don't, please let me know. Also, sidebar, some of you made it very clear that you found the whole thing very confusing. I respect that. It's an unusual, it's an unusual assignment. Most of the assignments will be much more mathematical than this. That will be a relief to some of you and will be harder for some of you. This one's unusual, so don't get too bogged down in it. But I will say, from here on in, with an assignment or with an exam, if you're confused about what it's asking, well, first of all, that's a big part of why step 2 of the 5-step problem solving method is so important. It's like really important to try to sit down and like actually before you go any further say like, what is this question asking? Like, because that can be very confusing in physics. I will say what you want to do for me from here on in is if you find something confusing, you got to do the 5-step method and you got to like write things. You want to be able to distinguish exactly when things become confusing. You want to say something like, I understood blah, 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 blah. But then when you got to blah, 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 then I lost you because I don't know what this word means or something. Like the more you can diagnose and isolate and define, identify your confusion, the more you will help me and help you start untangling the confusion. It's super. So don't just, to all of you, don't just say like, I don't get it. Like, try to break that down. And again, if I happen to be talking to some of you who did do that on this homework, I'm saying it with respect, not with shame. You, even if you got a 1 on the homework or something, because like that's all you were able to say, after this whole class, if it's more clear then resubmit it and you'll get all the points. It's not a shaming thing, but you do want to work on like identifying the source of your confusion. Okay, anyway, so I think that one was possible. I think task 2 is possible. I'm absolutely open to disagreement or cool discussion on it. But until that, if I don't see anything in the chat, which I don't, then I'm going to go on to task 3. And again, if any of you notice that anybody's in the chat or in the waiting room, just shout. Just say there's stuff in the chat. Or just say we're bored out of our minds. Can you please like juggle or something? All right, task 3. Yeah, task 3. So this one was now place 2 points of mass at 2 points in space at 1 point in time. Okay, and this one could engender some discussion. I'm going to say right now, like, so there was a lot of different answers on this. And actually every year there kind of are. Well, to cut to the chase, I personally think this one's impossible. I don't think this one's possible. What I don't think is that I can have this coffee pot. So I'm going to write that before, but I want to also address one of the most common reasons that people disagree with me. I will address because it's worth. I think if you've got 2 objects like a like this coffee pod and this pen, I don't think the center of each of these objects, like if I'm following the rules of this sheet, and sort of like the pre-rules of physics, if when I say pen, I'm really picturing a point of plastic at the center of this pen. And when I say coffee pot, I'm really picturing like a point of coffee grounds in the center of this thing. I don't think that I can actually have like a piece of coffee ground and a piece of plastic occupy the same point in space at the same point in time. I don't think we can. I think it actually is important that we can't. I also think most of you in the room, when I say it that way, probably agree. What I also know, however, to be very clear, one reason that a lot of people might have said this is possible is what I do agree. What I do know is that if one of your objects was a donut or like an empty cup, and the other object, wait, let me back up for a second before I even get to that. Remember again, we're picturing the center of each object. That's kind of a funky rule that we have to get used to in physics. But again, that point of that rule is we picture like one dot at a time in physics. Oh, there is someone here, I think. Wait, is someone in the waiting room? Oh, sorry. I think someone's in the waiting room. Yes, 2 people are. Pardon me. Hold on. Okay. In physics, it is. Okay. Can you still, is the screen back? Can you see the whiteboard? Yes or no? Is the whiteboard back, Antigone or Josh?
Yeah, we do.
Okay, great. Thank you very much. Okay. In physics, it's very important to picture one point of stuff at at a time, and 1 point of space and 1 point of time at a time. It doesn't mean we think, and it's often important to picture only one dimension of space at a time. It doesn't mean we're lying. Like a lot of the idealizations and optimizations that we make in physics that tend to throw people off in high school or send people running. Like, okay, quick sidebar. Like in high school, you start learning about things like, or in physics 101, you start learning things about like Newton's first law of motion, and like an object will keep on going forever if it's left to, if no force is exerted on it, no external force. So like a hockey puck is supposed to keep going straight at the same speed forever as long as we don't mess with it or hit it with a stick. And of course, when you first hear that, people are like, wait, hold on, maybe sort of a hockey puck, maybe if the ice is like super smooth, but like what about like a hockey puck on a rug? Like what about if there's, and then like that doesn't seem to obey the law. And then the teacher invariably or the professor is like, yeah, but we're saying if there's no friction. So then which we are saying, but then you get this idea. Oh, I don't know what happened to me early on was like, I'm like, oh, so physics is like full of crap. Like physics isn't really about the real world. Like physics can only handle situations with no friction. And like, as far as I know, in the real world, there's tons of friction everywhere. So what is it? So, okay, I guess physics is just another thing like math or like some magical kingdom where we just like memorize rules and it has nothing to do with the real world, even though I thought it was supposed to be a science. Like it can be a real turnoff to hear about these idealizations and these optimizations, such as no friction, or such as 1 point at a time, or such as one dimension at a time. Let me take this moment right here to urge you that freaked me out and upset me at first too. But we're not in physics saying, we are not saying that there's no such thing as friction. And we're not saying that there's only one dimension of space or that life exists in pixels. What we're saying is we're here to go from the ground up. We're here to establish the principles and practices of simple building blocks first. And then once we understand the simple building blocks, we put the building blocks together. Like we understand a brick, then we understand another brick, then we put the bricks together and we get a brick house. We're not saying we're not interested in brick houses. We're not saying that friction doesn't exist or 3 dimensions of space don't exist. What we're saying is we can only actually get a full understanding of friction or 3 dimensions of space if we put it all together one clean dimension at a time. So we go one step at a time. Okay, the long story short, in this sheet, as we now get to the things that I think maybe are impossible, the sheet has been asking us to picture the center point of mass is as the mass itself. It may be a weird rule, but it's a rule that we're consistently following through the whole thing. It's the same rule we used in number 1 and number 2 when we said they were possible. So now we get to number 3. Now we get to number 3, and I think it's impossible to have the center of this of plastic actually be at the same point in space and time as the center of the coffee grounds. I think that's impossible. I think you think that too, frankly. But what I also know is that many of you, especially the people that were taking this homework super seriously or being smart or were like looking for what's the angle, what's he going for here? Like where, I mean, they gotta be trick questions or something somehow. So some of you picked objects like a donut or like an empty cup, which I'm trying to look for right now, hold on. Or like a bowl. Like some of you said, okay, what if one of my objects is like this? And my other object is like this. And then you say, some of you, either on the paper you said it or in your head you said it, can't I put the center of this coffee pod in the center of this bowl? Now let me pause, and you can. So first of all, let me pause and say, if you thought anything like that, yay, like very smart, like, and I'm not being sarcastic, you can tell, I hope. If you thought of something clever, like basically where one of your objects like had a bunch of empty space at the center, and so then you put the other object in the empty space at the center. Oh, you are thinking, and that's, I mean, it's I don't know if it's brilliant, but it's like super smart. And it also shows that you like are knowing what's going on in the whole questions. But now and again, of course, you got full credit on the homework no matter what. And if you put something like that in an exam, you get full credit. Like you're definitely being thoughtful. But now let me say, with the same respect that you showed the assignment by doing that, let me show you the respect of saying, okay, but what does it illustrate that you had to do that? If in order to put the center of one object in the center of another object, if you had to carve out one of the objects, if you had to turn one of the objects into a bowl or a donut or something, then what you're really doing cleverly is you're creating space for the other object, right? What you're saying is the center of one bunch of things, the center of some coffee ground is now in a center point, is in a point in space that is not occupied by any other stuff, right? It's super smart and clever. It's so smart and clever that I think it actually illustrates the same principle that I'm saying when I say that this doesn't work. What is it that I'm saying? I'm saying I don't think literally 2 points of mass. I don't think 2 points of stuff, of thing. We'll define that more rigorously when we get to the end. But I don't think you can literally have two things occupy one space point at one time point. You certainly can have one thing occupy the center of another object as long as that center is empty, right? But I don't think you can have two things occupy one point in space at one point in time. I'm now talking intellectually, not academically, meaning I don't care what you put for this, you got full credit. Don't worry about your grade. There's nothing. And if you put the whole clever thing that I just described or some version of it, or even if you were picturing it, then you're so in the right class, like really. But for the purpose of moving on, I think if you interpret the question the same way that we interpreted the other questions about centers of stuff, I think number 3 is impossible. Now, I'm going to pause for a second. I still have to go on, obviously, to the other two. Is there any, are we okay? Can I get any indication even, oh, and hello, Carla with the avatar. That's awesome. And again, Lalia Too Late, thank you so much. And Takarub, I'm not sure if I acknowledge, thank you for the avatar. And Sadie, thank you for the, can I get any kind of electronic acknowledgement that, am I okay what I'm saying there on number 3? Why I think the answer is impossible. Thank you, Josh. That's awesome. Okay. Oh, and thank you, who's that? Roland. I totally appreciate those of you who are not on video, which again is fine, but showing the electronic. Thank you, Takarub. Thank you, Caitlin. Thank you, Antigone. Okay, great. All right, thank you. This is like, thank you, Amelie. And is it Amelie? You could thank you, Carla. And please, Amelie, tell me in the chat if I think I'm saying it wrong. I know I'm saying it wrong, actually. Again, I know you all think this is Physics 102. As you can tell, though, it's really group therapy for me. And, you know, we want to make it worth it. I'm just kidding. Okay, so that's number 3 then. Oh, I am saying it right. That means I'm saying it right, Amelie? Okay, great. I won't push my... So it rhymes with cadaver bound. No, okay. All right, great. All right. So now we go to task 4. I'll try to speed this up a little bit more. I'll try. All right. Task 4 now gets awkward. And now we're on to the one object thing, right? This is place one point of mass in one, in one point of space in 2 points, well, I should say at two points of time, 2 points in time. Okay. Now this one, again, I think it's awkward for you. May never have, it's sort of a mind bender question, maybe to some of you, because, you know, we don't usually, I don't know why, but we don't think of things this way. But it's asking for 1 point of mass to be at it's asking for 1 point of mass to be at 1 point in space, but at 2 different points of time. I'm going to say right now, oh, I think that's possible. I definitely think that's possible. In fact, I think it's so possible that I think there's 2 different. Oh, and I should also say a lot of you said it wasn't. So number 1, hopefully, I'm going to tell you now why I think it's possible. And you tell me in the chat if you don't buy it or whatever. And I'd love to have discussion about it. I would. But to cut anyway, and I'd love to hear anyway. I think it's possible. I think there's 2 different ways that it's possible, actually. I think one way that it's possible is, here's my thing, right? Let's say here's my thing, number 1. So number 1 thing I can do is I can go like this. I can go d, right? Like Like I can, right? I can have it at a place. And if you're smiling because of that dog, I agree with you. I should totally mute that dog. Okay, here's a thing. It's not there. Now it's there at the same place, right? So it's at the same place at two different times. And again, maybe I'm really spazzy. So maybe the second time, like maybe I drink too much coffee. Duh. So the first time I put it there, I put it here. And then maybe the second time, like I try, but I'm like, so, but if I keep doing this enough, it's eventually going to hit the same place sometime later. Like no one's saying it has to be on purpose. It's just saying, can it happen? Right? I'm pretty sure I can arrange for this to happen, no matter how spazzy I am. So number one, and then some people, some years even get into like interesting things about Earth's rotation and that the Earth moved so that, okay, but even all that into account, maybe that means it's harder to do on purpose than I think. But the fact is, something can be somewhere, and then later it can be there again, right? It can. Or what some of you said in the sheets, and I also think it's super clever and just as legitimate, hello, is you can go like this. Right? Like here it is now at that point, and also here it is at the same place later. Like it happened to have been there at all the intervening moments. Who cares? All of them count. You can have a thing at two different places. No, sorry, at two different times at the same place. I think. So I think task 4, is possible. I really think you should stop me if you don't like that, and I won't argue with you. We'll just discuss. Wait, I'm just looking. But are people cool with that? That's a yeah, sort of that. Are we gonna see? Then this is why people don't show video too, because I keep. Oh no, I just lost you all. Did I just? Oh, there's stuff in the chat. There's stuff in the chat. Somehow my screen just told me that. Wait. Oh yes. Oh, okay. That was from before. Okay. Cool. I think it's from before. Okay. And someone's in the waiting room. And yes, thank you, Madonna. Okay, and someone's in there. Holy smokes. Hold on. Waiting. Sorry. I know I know I'm boring myself too, believe me. This is not going to get an Academy Award. How can I get? But it is going to get a Gus Johnson satire. Wait, I wish Antigone wasn't on mute because whatever she just said, I bet was priceless. Okay, but wait, how can I get the waiting room? Okay, so those people should be back. Okay, and I'm looking at the chat again because it looks like there was more in the chat. Oh, no, that's all. Okay. Oh, a lot of people in video. Thank you. Oh, hello, Sadie. Awesome. Thank you for bearing with this train wreck. Okay, so back to, so that was task 4. I believe it's possible. Now, finally, we do task 5. This is place 1 point of mass in 2 points of space at 1. Okay, so this one, to cut to the chase, this is just an inversion of task 4, right? To all the same words, but like in a different order. Task 4 was 2 points in time, 1 point in space. We said that's possible. This one is 2 points in space, 1 point in time, and I'm saying that's impossible. And I think most of you agreed on your sheets. Like again, we're following the restriction that this entire pen I'm identifying in my mind as 1 pixel at the center of the pen. That hello, welcome back. Hello. I'll be off soon. Thank you. Okay. Yeah, it's not my right. You get to say hello quick. Okay, hello. Okay, that is my permanent lab tech and esteemed adjunct professor. Okay, now I'm gonna go. Okay, you said hello. All right, awesome. Thank you. Okay, awesome. Okay. Okay. Oh wait. So I'm like, okay, I'm glad that at least elicited a smile. You're much more generous than I am. Okay. So I'm not, there's a lot. Wait, are you guys at John? Oh, I'm guessing, are Antigone and Sadie in the same place at the same time, so to speak? If that was, please no dog. Okay, now there's a dog here too. Okay. Are you guys, all right, it's probably to their benefit that they're on mute. I'm wishing they weren't on mute because I want to know what's going on, but okay, it's not my business. Okay. I feel like honestly, has anybody in this room ever felt like their spiritual fly was permanently open? I'm just saying. Okay. Um, that's inappropriate. All right. This pen, this pen is identified by the point in the center of it. So I know one end of the pen is here and one end of the pen is, but like that's not what we're talking about. We're talking about the center of the pen. The center of the pen cannot be in two places at the same time, right? Notice how just inverting the language seems to have made, well, so I'm saying impossible. I'm saying this one's impossible. And I think most of you agreed with that. Now let's summarize. We're almost at the end of this. We're almost landing this plane, which is hardly a 747. Notice when we said two objects at one space at two different times, that was fine. But then we said two objects at one time, two different spaces. Sorry, that was fine as well. Back up. When we say one object at two different times at one space, that's fine. One object at two different spaces at one time, that's not fine. All we did was switch the words, which definitely indicates that even though there's some kind of deep similarity between space and time, apparently there's something very different about space and time, which most of you were getting at in your answers to the other questions. Like, we can have an object at two different spaces at one time. Sorry. We can have an object at two different times at one space, but we cannot have an object at two different spaces at one time. Something about that indicates some kind of fundamental distinction between space and time, which we have to get at. But more to the point, the real point of this whole sheet, if you're in agreement with me that 3 and 5 were the tasks that were impossible, the purpose of this whole exercise comes now. The purpose of this whole exercise, I'm going to skip, all of you had very interesting answers about what space and time are. We'll see more and more about what space and time are as the year progresses, as the semester progresses. But the real question is, okay, so I want to answer the question now, what is a particle? And I will tell you, this is worth paying attention to now because all of you had super interesting answers to this question. All of your answers are very, very different. And many of you said things that were like the ramp up to what I'm about to say, or a very good foundation for what I'm about to say. But I'm about to say something very specific now that was not on any of the sheets. So it's like worth hearing. Before I say it, let me remind you, this is physics. Physics is all about studying motion through space and time, specifically any, and I think we said this last time, I'm pretty sure, I hope we said this last time, any motion through space and time that is measurable, reproducible, mathematically analyzable, and predictable is the province of physics. If I think I said that last time, but if I didn't, please catch this now. I'm saying, this is not the answer to the question yet. First of all, I'm saying any motion, anything at all that moves through space and time in a manner that is measurable, reproducible, mathematically analyzable, and predictable anything that moves through time and space in those ways is part of physics. Physics is the study of all of anything moving through space and time in those ways, in a measurable, reproducible, analyzable, predictable way. So that's anything that. So why I'm saying that before I give the answer to this question is a lot of you picked up on the theme of the sheet. And by the time it got to what's a particle, a lot of you wrote something like a particle is something that occupies space and time. Or even like some of you even wrote like a particle is something that's like exists in space and time in a measurable way, or something like that, or a particle is something that takes up space for a certain amount of time or something. These are all very clever answers, and they definitely do show that you're paying attention to the sheet. But I'm going to be more specific than that in my answer because I think anything in physics has to occupy space and time in a measurable, reproducible, analyzable, predictable way, right? So in a way, what I want to caution you is that for a lot of you, your definition of a particle, in a way, was actually a definition of anything that could ever come up in physics. And some things come up in physics that aren't particles. That's what we have to get to here. So I hope that's clear. What I'm going to say is what makes a particle a particle. What makes a particle, I'm going to, okay, wait. So first of all, in physics, everything we study involves, so anything in physics involves something moving. This is the thing I just said. I'm just rewriting that. Through space and time in a measure. I mean, I said it a million times a second ago, but okay, so just a reminder here, the thing you just wrote down. So anything in physics, anything that moves through space and time in a measurable, reproducible, analyzable, predictable manner is physics. Okay, anything is. I'm going to turn the page now. If you want me to turn back, just let me know. But a particle specifically, and notice I'm emphasizing anything that moves through space and time, like falls under physics. What I'm ultimately trying to get at here is like there's different kinds of things. A particle is a specific kind of thing. A particle, and again, tell me if you want me to move back, but a particle is, first of all, informally, this is the informal definition first. When we say particle, it could be, I don't care, it doesn't have to be a grain of sand. A particle could be small, it could be big, it could be an electron, it could be a planet, it could be a baseball, it could be like a Maserati. A particle could be very big, but what it means to be a particle is a very thingy thing. This is the informal definition, of course. A particle is a thingy thing. Now, what do I really mean by that? Well, informally, I mean it's like what many of you said in your homework. Like, yes, I mean like tangible, countable, discrete, like identifiable, separatable from other particles. I mean about massive, material, all these things. But specifically, what I really mean, formally, what I mean, a particle is a discrete countable, that's really what discrete means, but countable material which cannot perform task 3 nor 5. This is, now let me be very slow about this. And if that doesn't sound formal enough to you, if you're like, wait, task 3 and 5, that doesn't sound like science to me. Really, the scientific term for this that you learned in chemistry. What I mean by a particle is a particle must be localized and obey the Pauli exclusion principle. Now I have to break this down. Also, tell me if you can't read the handwriting or whatever. I'm going to work backwards here. First of all, for those of you who like want real science, of course, I'm just being honest. Like the actual science of what I'm saying is that from here on in, when we say particle, and you can even, if you really want the technical term for it, what I mean by particle from here on in is a type of particle known in particle physics as a fermion, as opposed to things that are known as bosons. Now that gets very technical. It sort of comes up in the Oppenheimer movie, kind of, but not really. I mean, you're welcome to go crazy looking that up if you want. I'm just telling you so that you don't think I'm like making crap up or that I'm like not insulting your intelligence. So the technical thing I'm saying is that for something to be a particle, it has to be localized, which means it has to exist at one point in space, at one point in time. Okay. And it has to obey the Pauli exclusion principle, which means it can't share that point in space at that point in time with another particle. Okay, so you've heard of the Pauli exclusion principle in chemistry, I think, or either in high school or early in college. Like the Pauli exclusion principle is that whole deal of why, like, the most number of electrons you can ever have in a suborbital, right, is like 2, and if you even have 2, they have to have different spins, all that stuff, that which we're not trying to get all into right now. But I'm just saying there is real science behind what I'm saying here. I'm saying this, that from here on in, when we say particle in this class, we mean a certain kind of thing. We mean a kind of thing that's really thingy. We mean a kind of thing that on an intuitive, human, regular, everyday, like non-science level, people would think of as like tangible, as material, as graspable, as like solid, as massive, as material, right? Like informally, when we say a particle, we tend to mean these objects that people can relate to as really being thingy, like really feeling like things. But what do we really mean by that in science? What do we mean by a thingy thing? What makes a thing thingy? What makes it that some objects seem really massive or countable or separatable from other objects, all that, or material? What actually makes them this way, or what the actual defining property is, what it really means to be thingy. And I'm yelling because now we're really into physics now. Like what it really means to be a particular object, to be a particle, is that you cannot be, it's not just that you occupy space and time, because everything in physics does. There are things that occupy space and time that don't obey this rule. That's what I have to get to next. But what I'm saying now is if something is a particle, it cannot be at 2 space points at one time point, and it can't share one space point at one time point with another particle. I'm saying that's not a feature of space and time. I'm saying that's a feature of certain kinds of things that live in space and time. Certain kinds of things that live in space and time live that way. They don't share and they don't dislocate. Now, all of this right now, all of what I'm saying would perhaps be a lot of weird language for something that you already knew and was already obvious. And you're like, okay, fine. So yeah, like, right, a bowl is a bowl and a pen is a pen because they can't share a space. Like, I get it. Like they knock off each other like that. Okay, I know you get it. But the reason this is also interesting to me is that this is not all of physics. Physics is about stuff that moves through space and time. In 101, sorry. Physics 101, which you already took, of course. Physics 101 was about the motion through space and time of particles. The reason this is all obvious to you, in a way, I mean, I think, is that physics is always about the motion of stuff through space and time, and the kind of stuff that you've already studied moving through space and time that you already studied in Physics 101 was exactly particles. Whether they were balls on inclined or carts on inclined planes or bobs on pendulums or masses on springs or planets, all of those things you were studying in Physics 101 were particles. So all of this is like ho hum. But what I'm here to tell you is that was a special kind of thing you were studying. There are things that move through space and time. Well, the key point here is there's tons of stuff in the world, in the scientific real world, that moves through space and time in a manner that, okay, whatever is going on at John Jay right now, well, anyway, whatever. Okay, there's tons of stuff that moves through. I mean, do I know the person that you both are? All right, whatever. Okay. There's tons of stuff. But see, it all works because every time I make a joke about that, they know it. So they're obviously paying enough attention to me that it's like all anyway. And they're probably never going to show a video again. So I'm so regretting that I'm doing this. But okay. There's tons of stuff moving through the world, through space and time, that absolutely violates Rule 3 and Rule 5. Like, this is, to me, the punchline of all this. 3 and 5 are impossible for particles. They're not impossible for everything in the scientific world. And frankly, all the things in the scientific world, not all the things, but the stuff, the entities that move through time and space in a manner that is not restricted by 3 and 5 is ultimately what we're here to study in 102. Physics 102. Like this, so what makes all physics, what makes both classes physics is it's about motion through space and time. What makes the two classes different is the actual things that we're studying moving through space and time. Physics 102 is about the motion is ultimately about, we start off with a review sheet about mass on a spring, you'll see why, but it's ultimately about the motion of non-particles. Ultimately, what Physics 102 is about, we here study the motion of unthingy things. We here study the motion of things, entities that are real, that exist, that occupy space and time in a measurable, predictable, analyzable, reproducible way. But we study here entities that are not tangible, not material, not countable, not discrete, not solid, we study here ultimately the motion of entities that can be in two places at once and that can co-occupy one place at one time. Oh, so I'm going to turn it to you for a second when I'm looking at the time. So I'm trying to say something now that I think is not obvious. I mean, I might be saying it so many times that maybe it's obvious now, But the new piece of the reason you did homework 1A, even if it was silly or fun or easy or confusing or easy, the purpose is actually to get us off the ground and realize what the purpose of this whole course is. The purpose of this course is to study stuff moving through space and time in a non-tangible, non-material way. The motion of, we're here to study, the motion of immaterial entities. Totally real, but not material. Kind of interesting. Kind of more abstract. Kind of hard if you don't realize that that's what we're about to do. I'm going to stop for a second and ask you, and this is why I think 102 is, frankly, is ultimately more interesting than 101. Once you know if you know what you're getting into. So let me stop and ask, can anybody in the room, maybe someone who's showing video or maybe not, but can anybody in the room give me an example of something in the real world, that can like share a point in space at a point in time with another thing of similar character? Like, can you give me an example of something where two of them could actually be in the same place at the same time? Or put another way, give me an example of something that seems always to be in more than one place at one time. Like an example of an immaterial, non-particular entity that's non-material, non-discrete, but actually exists in science. Can anybody give me an example of something like that? Like a real example.
Something like Wi-Fi or Bluetooth count.
Wow. Awesome. First of all, awesome. Okay, she just got like a bajillion points. And I mean, Antigone just got like a bajillion. And thank you. And good sit. Oh my God, did that third person that you guys keep talking to tell you the answer? No, I'm just totally kidding. Okay. No, that's awesome. Wait, what? How close are you? Like literally in the same chair? Okay, no, I'm not. Okay. Whoa. Oh, that's so weird that you just did that. Okay. Well, I'm glad. All right, no, that's good. It makes it feel more like a class. That's awesome. I hope you all study this way too. Remember, anyway. Okay. So she just gave a great example. So Antigone just gave. So my question again, and someone should put in the chat if they don't understand the question, because now we're getting into stuff here. Like we are getting into the real issues here. I just asked, is there anything like in the real world that sort of like two of it could exist in the same place at the same time, or that it's like seems spread out in space time? And what Antigone said was like, she said like, well, what about like Bluetooth signals or Wi-Fi signals? I'm not sure if she used the word signals, but she said Wi-Fi or Bluetooth. And I'm going to say that, yes, that's maybe a very hard example. To be super honest, that example is just hard enough that it comes at the end of our class. Like we're going to build all the stuff so that we can finally sort of understand what's going on with Wi-Fi, more particularly than Bluetooth. But these, what she's talking about, what Antigone's talking about, which is definitely an example. I mean, definitely does answer my question. She's talking about something that we ultimately call electromagnetic radiation, or let's even say electromagnetic waves, especially in the case of Wi-Fi. That's what she's talking about. Well, and Bluetooth. Bluetooth is very specialized, but yes. So absolutely, electromagnetic waves are an example of something that's real, something that moves. I mean, I can tell you what speed they move at, something that moves in a predictable way. If it wasn't moving in a predictable way, we wouldn't have all these devices like working, although of course my computer is not working, but you know what I'm saying. They're obviously part of reality. They're not Harry Potter, Wi-Fi and Bluetooth, but they're definitely not material. I mean, Wi-Fi signals move. Like you all know enough to know there's a tower somewhere. Things move from the tower to your device, or from your device to the tower. Like motion's involved. Space and time is involved. Now the time is very short. That's why we love Wi-Fi and everything. Like these signals, and I'm going to call them signals, they move very quickly, but they sure do move at a certain speed, which is predictable. Otherwise, the whole thing wouldn't work. So, but they're not material. You can't touch a Wi-Fi signal, and a Wi-Fi signal doesn't bang another Wi-Fi signal out of the way, right? Wi-Fi signals interfere with each other. They share space with each other. We'll get into all of that. But she's absolutely right. In other words, absolutely. In fact, I'm going to write. Okay, hold on. So yay, Antigone. And Again, remember, she can submit to the portal that says like for right or for wrong. There's a million places. She used her voice. She's got her video on. I mean, she's got like 20 points for just like that, or something. Anyway, examples. So one, I'm gonna write it as Wi-Fi. I know she also said Bluetooth, but I'm just gonna keep it as the technology is similar enough. But Bluetooth is like a brand, so I'm just gonna leave it as Wi-Fi signals. And a key word there is signals. Now I'm gonna ask I'm gonna name some examples myself too, but as I said, that's just complicated enough that it sort of comes at the end of the course. Can anybody think now that like Antigone broke the ice? Can anybody think of anything maybe even a little bit less technologically advanced? Like I would argue there's at least one phenomenon that you all know that existed like in caveman times and certainly was understood in like even the 1600s, like something that exists, that moves through the world, that makes a big difference in our lives. Like it matters, but it isn't matter, and it's a little bit more oldie schooly. Can anybody think of basically I'm saying I think there's an even lower technology example that just maybe people can relate to. Some people might be able to relate to. And we're using it right now. We are using it right now. Of course, we're using technology to get it from me to you, but one hint is that even my son was in the, my younger son you saw was, oh, I just lost you. Where'd you go? Oh, there's something in the chat. Wait, there's something in the chat. I don't know how that happens. Okay, one second. What's in the chat? Oh, interesting. Interesting. Okay, I like what Madonna put in the chat. I don't know how long it's been sitting there. I apologize. Now, Madonna's going to get a lot of points for submitting that. Now, I think we all know each other well enough at this point. We're all so close that I'm going to go on a limb and say, I love what Madonna put in the chat, and she can submit it to all, like to for the right or wrong thing. But also I'm going to say with total respect, I think I respectfully disagree. And I think she can therefore submit it for extra points for the be wrong, be really wrong. It's not really, really, really wrong, but I'm actually going to say that atoms, here's the thing. I think atoms are particles. I think an atom, even a simple, like a hydrogen atom, like it has a proton, it has an electron, or a helium atom has like 2 protons and 2 electrons, etc. And the fact is, I don't think, now it's hard to see this, but I think the point of atoms is that they are material, discrete, countable objects. Like I don't think you can literally have a hydrogen atom at a place, at a certain place at the exact same time that you could have literally another hydrogen atom. More specifically, I don't think you could have like the protons of the 2 hydrogen atoms at the same place at the same time. I don't think you could have, like you could have some of the space overlapping, but the centers, I don't think you could have at the same place at the same time. This is not to dismiss Madonna. I mean, but I do want to make, does it make sense? And so she can get extra points for the guts that she had to say that. But does it actually make sense? And I think what I'm looking for here is things that can literally be in the same place at the same time with other such things, or things that are like necessarily spread out in space. Am I making any sense? I don't know if Madonna wants to. Okay.
Yeah, it's very clear. Thank you.
Okay, thank you. I appreciate you being very polite, and you get tons of. Are you, just out of curiosity, are you also with John Jay with Antigone and Sadie? I'm just wondering. Or
Me?
Yeah. No.
No, I'm not from this college. I'm an e-permit student.
Oh, right. Okay, I'm sorry. Oh, so thank you. Okay, well, I'm so glad you're joining us. Okay, do you mind, just a quick human thing, do you mind reminding me which college are you from again? I forget. You told me, but I forget.
I am from the CCNY.
Oh, awesome. All right, that's a hard play. I got one of my degrees there. Well, bless you for being here. That place is hard. Okay. We're all hard in different ways, but okay, anyway, well, I'm glad you're here. Okay. Say hello to all the professors that almost failed me. Okay. No, they didn't fail me. I almost failed myself. That's all. But I didn't. Okay. What I'm getting at here. Oh, gases. Someone put, I think it was Carla. Now, gases, that's a really good thought too. I'm going to get right to the point and say, you're going to get a lot of points in the same way that Donna did. I love what you're saying. It definitely shows that you understand the question. Gases seem like 2 gases seem like they can occupy the same place at the same time. It seems that way because gases are even more abstract than liquids, and liquids are even more abstract in a way than solids. But it's worthwhile that we're having this discussion Because if you think about gases, there's two things to think about. Number one, ever remember, like from when you were in seventh grade, this always went over my head in seventh grade or third grade or something, but they always say that the three phases of matter, or the three states of matter, they call them, are solids, liquids, and gases. Now, I know we all memorize that a million times, and okay, the three states of matter. It didn't occur to me till I was teaching physics for like 5 years. Suddenly I was like, oh my God, the three states of matter. They're actually saying that solid form, liquid form, and gas form are three different forms that matter finds itself in. They're trying to tell me that a gas, even though it seems really like everywhere, ephemeral, like air, it just seems like it's just there, whatever. They're trying to tell me that a gas is actually material, which they are. They're trying to tell me that a gas really is made up of particles. The thing about a gas is, it is certainly different from a liquid or a solid in that, you might all recall, a gas is something that does not have definite shape or definite volume. Now that's weird. I mean, that really is weird, right? It means, right, like a solid has definite shape and definite volume. A liquid has definite volume, but not definite shape. So liquid always takes the shape of its container. But if it's 30 milliliters of milk, it's 30 milliliters of milk. You pour it from you pour it from a thimble into a beaker, whatever, like it'll take different shapes, but it's just going to be those 30 milliliters. The crazy thing about a gas is you have a certain amount of gas, like 30 cc's of whatever, nitrogen gas. And then you open the container. Now it escapes all over the room. Not only does it take the shape of the room, but it takes the size of the room. Now that is crazy that a gas can do that. That just shows that whereas with a solid, all the molecules are actually bound together. And then in a liquid, all the atoms, even if not the molecules, the atoms are somehow bound together. In a gas, the atoms are not even bound together. The atoms are free to just go whoop, and take up any size they want. So that does seem very abstract. Like, I'm very glad someone just brought this up. Gases seem very abstract, and it almost seems like we can't feel them or touch them or da-da-da-da-da. But here's where this distinction of particle, this definition becomes so important. The fact is, a gas still is something, even though it can be any size and it can be any shape. That wasn't our rule. Our rule is, can a particle, can a element of gas, can a piece of gas, an atom of gas, be at two places at once or occupy one place at one time with another element of gas? And the fact is, we know it can't, and here's why. And not only do we know it can't, but we take advantage of this fact all the time. When you blow into a balloon, right, or do anything like that, when you blow into a balloon, you're putting more gas called air into the balloon, right? And even though that gas seems so abstract, and even though it seems like you can't feel it at first, you definitely feel its effects when you blow into that balloon. The gas pushes the plastic or the latex or the rubber or whatever out of the way, right? The rubber says, whoa, a gas molecule or gas atom, like a air or in the carbon dioxide molecules coming in. So the plastic moves out of the way, the rubber moves out of the way, it stretches. And so the balloon gets bigger and bigger precisely because the gas won't share space with other matter. The gas actually is matter. And I'm not saying all this to like argue with Carla. Like, I'm thrilled she brought it up. And I know a lot of other people were thinking that when she brought it up, and they every semester they are. It's not at all dumb that Carla brought that up. It's like, but it's very revealing that even gas is made of particles, meaning entities that won't share space at a given time. Because gas won't share space with even another gas, that's why we can make things called pistons, right? We can like make cylinders that have like little like rods in them with little caps, and then we put gas in the cylinder, and then the rod goes up and it turns a crank and it turns an engine. Hence, with a little bit of a spark of heat or something like that, we can get a piston to expand and drive a car. You see what I like? We literally rely, I don't know if that was too fast or too, but I'm saying it turns out gas really is material. It really is particular. And we take advantage of the particular nature of it every time we put a piston in some kind of engine and then make something move through the macroscopic world. So again, this is not an argument. Remember, there's a portal literally so Carla can get extra credit for having the guts to like put this interesting idea into the room, and so that I can sort of like expand on it. No pun intended. But gas is is particles, and maybe Carla could get even more points if she puts into the chat like, yes, I understand, or no, you didn't ruin my life by or whatever. If she puts something like, yes, conversation closed, she'll get even more points. So she already did. Awesome. I'm sorry. Okay. Sorry, I can't see the chat, but I see that for some reason. All right. Great. I see. Oh, she did. So if now I see. So if two gases are in the same area, the chemical. Oh, yeah. Good point, Carlo. The thing about the two gases in the same in the chemical. Yeah. Oh, okay. I understand. Okay. Cool. Awesome. Yes, you did. Good talk, everybody. All right. And it's 4:40. So we're actually vaguely on track here. Okay. Awesome. All right. Oh, and there's Sebastian. Oh, there was Sebastian. Oh, Sebastian just got points. Okay. It's like a oh, and he got more. Awesome. Great to see you. Awesome. And Yichan's been getting quiet points this entire time. Also, he takes amazing notes, I can tell, or I'm guessing, so he can submit those for points too. Okay. Am I singling people out? Yes, but only for compliments. Okay. Wait, who else have we known? We've heard from a lot of people. That's good. I feel like you guys are. Do me a favor again. Well, no, don't do me a favor. I'm gonna give you another example to get this thing going. I think an even more like direct, intuitive example. Well, I'm going to just give you examples in the order of this course. Here we go. Oh, wait, or did someone just put something in the chat? No. Okay. Oh, someone's here. Hold on 1 second. Okay, I know someone's here. Bear with me for a second. Okay, you might lose this board for a second while I let someone in, but then I'll go back to this board. Bear with me for a second because I think someone's here and I never know how to do this. Gus Johnson calling just codes. Okay. Oh, and the chat. I'm looking at the chat. Oh God, there's so much in the chat. I'm so sorry. I did not see all this. Okay. Because there's two different chats. Okay. I'm looking at the chat. Somebody in direct chat put internet. Very good. Yes, internet, absolutely. Communication, word, speaking. Okay, well, you might have seen, I'm gonna go back to the list I was just writing. Communication, word, speaking is awesome, especially if you mean the sound aspect. Definitely. Electricity, definitely. Now, energy is a good larger word for all of this, which we'll talk about for sure. Heat is a great answer too. Heat is perfectly legitimate answer. Heat absolutely is an answer. The only reason I didn't write it in my list, you can add it to the list. All of these things are legit. Heat is very concrete, like and super legit. I didn't add it to my list only because when I turn back to my list in a moment, since I'm now looking at the chat, you'll see that everything I put on the list is actually what we studied in the course. And that's really the point of this whole discussion. But okay, I now see everything else in the chat. I think, forgive me if there's other, and the reason there's two different chats because I'm like two different people right now. So I don't know which one you're supposed to send them to, but all right, going back to the board. Okay, Here's the board. You could put heat in there too, absolutely. But the things that assuming you can see the board, which I hope you can. Wait, it's so funny. Okay. Let me know if you can see the board, but all of these examples on the board, they're all examples of unthingy motions, and they're all the unthingy motions. They're all immaterial, abstract, non-tangible, non-countable, non-massive. Again, I think the key word is immaterial. These are all immaterial motions, and they are the purpose of this course. We start with the mass on the spring because ultimately we find that all of these things in some way or another boil down to the understanding. Like ultimately, if we understand how a mass on a spring vibrates back and forth, and that is a thingy thing. A mass on a spring is a particle. Technically it's in the province of physics 101. But the purpose of this course is if we study vibrations, oscillations hard enough, if we understand the math of oscillation, then we put together a bunch of oscillations in a very particular mathematical way. And what we get are things like waves and fields and radiations, all of these higher level motions, these more abstract motions that ultimately make up the topics of this course. Very quickly, just to establish my point, if I'm losing everybody, like just to take sound, for example, like I'm not, well, can anybody have the guts to get points? Can anybody right now, can anybody unmute and right now while I'm talking, just say anything you want while I'm talking, like literally interrupt me for the sake of a demonstration. Just while I'm talking, just unmute and just say anything or laugh or do any noise you want. I think I heard one keep. Oh, good. Thank you. You can keep going also. Okay, thank you, Antigone. And thank you. I saw someone did it and then it was Antigone. I don't know who first, but it was Carla. Okay, thank you. Now, that's good enough. Now, any of you in the room who heard, if you even for one moment heard my voice and Carla's, or if you heard for one moment my voice and Antigone's, think about that for a second. That means at your eardrum, there were two sounds occupying one space point at one time point. There had to have been, right? Or if you've ever played a musical instrument or listened to music, if you've ever heard in your life a chord, and I'm sure you have, like if you've ever heard two notes at once, and you know it sounds different from one note followed by another note, or if you literally, even if you don't know anything about music, but you listen to music and you've ever heard someone singing while someone's playing the guitar, or someone rapping while there's a beatbox, or like whatever, then you know that like that's the whole point of music, right? The different sounds hit you at the same time, and they really do. It's not an accident, and it's not a technicality, and it's not some small weird detail. It's like the whole point of music, right? Like a sound wave can be at the same point at the same time as another sound wave, and when they literally share space. And if you remember anything from high school or maybe early physics, you know that when one wave hits another, they become momentarily one big wave with like twice the amplitude, or if it's a crest hitting a trough, they become one small wave with like no amplitude. But right, that's called interference. It can be either constructive or destructive. Waves can do this. Energies, if you like, can do this. Fields that we're going to learn about later in the class can do this. A lot of stuff in physics can literally share space. Unlike baseballs, which bounce off each other, waves don't bounce off each other. They share. That is fundamentally different. Waves are real, but they're not particles. Fields are real, but they ain't particles. And radiation, the combination of electric fields and magnetic fields ultimately makes up something we call electromagnetic radiation, and the shorthand word for that is light. And all the stuff that you guys were talking about, Wi-Fi, Bluetooth, internet, which we get to at the end of the course, all of that stuff is example of things moving through space at light speed, a bunch of energy or moving through space at light speed and being very, very real and very measurable and very scientific, but not being restricted by rule number 3 or rule number 5. So to bring this full circle and then move on, the point of rule number 3 and or task number 3 and task number 5, those did not show us something about the binding nature of space and time. They showed us something about the bound nature of particles. When particles live in space and time, they can't do number 3 or number 5. But a bunch of stuff lives in space and time and moves through space and time in a predictable, scientific, measurable, analyzable way. And that stuff that moves through space and time in a measurable way, but in a way that is not restricted by task number 3 and task number 5. The larger word for all of that is information. So we're about to wrap up here. We'll wrap up this part. I'm saying in sum, in physics 101, we studied, or whatever you called it at your school, the first class you took in physics, we studied the trajectories of particles. In physics 102, we study the propagation and propagation is a fancy word for flow of information. What we're ultimately studying here in physics 102, ultimately, we still have to get to it, but is we're not studying how a discrete object moves from here to there. We're studying how information, whether you want to call it waves, and sometimes that's appropriate, whether you want to call it fields, sometimes that's appropriate, you want to call it energy, sometimes that's appropriate, but the underlying thing to all of it is we're studying how raw information, like quantities, like numbers or vectors, we're studying how raw information flows from one point in space and time to another point in space and time. And it's all built sorry. Okay, we're finally getting to, so this course is ultimately about immaterial motions, motions of stuff that doesn't seem material. Okay, like again, like sound, like electricity, like things that again I ultimately find more exciting, but they are more abstract. I mean, that's why I think they're more. But again, so everything we do in this course ultimately is we're looking at how immaterial things flow, or immaterial entities flow from. Ultimately, we're looking at how raw information flows from one point in space and time to another. Now, oddly, what's bizarre is it is all science. It's all right. It's not Harry Potter. I mean, with all due respect to Hermione and everybody else, it's not magic. It's science. So it's all tethered to stuff. It's all like connected to stuff, to observations and measurements that we can make with material things that we're used to. So it turns out that the mathematics and the descriptions and the laws, the practices and principles of all of this electricity, sound, fields, all this stuff, all starts with, it's all based on the mathematics that describe oscillation. It turns out that basically how we build waves or how we make the internet ultimately is lots and lots of things oscillating together in a certain pattern. So we start the whole course by having to understand oscillation, or what we call harmonic oscillation. Of course, that's what you've been doing in the lab for the last 2 days, 2 weeks. So wait, I'm going to look at the time. So we now have 2 more. So we're making tracks finally. I know I'm just like yammering and yammering. I'm going to turn it over to you. I really am in a minute. But we've got 2 agenda items left. I'm just looking at the time. And again, I'm not going to take a break because I'm finally feel like I have some momentum here. But if you need to take a break for 7 minutes, I totally understand. Just do it. I mean, just, and then you'll, or whatever is good for you, just do it. I won't be insulted, but I'm going to keep going. Hold on, I'm just looking at the time. Okay, so it's 4:50. So I'm going to say right now, in the interest of continuity, you turned in your homework 1B. I know that. I believe, well, correct me if I'm wrong. Okay, pause for a second. I believe, tell me if I'm wrong, that by the end of last class, finally, after a lot of yammering, I was able to go over question 1 just to start you off and show you what the 5-step method was. Is that correct? In the last class, did I go over question 1 of homework 1B and show you the 5-step method? Uh-oh.
Yeah.
For sure. Yes, and take it. That's a, or, wait, are we,
Yes, yeah.
okay, all right, cool. Oh, that's Mira. Thank you, Mira. I totally hear you. See, okay, great. Thank you all. Okay, so, and then you did your best and you turned it in now. Now, part of my job is to start going over that, of course. And I will not leave you high and dry. And I'm going to give you lots of feedback on whatever you turned in. Like that homework 1 is particularly, or let me be clear. Homework 1B is particularly important because it will make sure we're all on the same page before we get to an exam. Like you'll hopefully get sort of extra detailed feedback on that one. We're going to make sure that everybody's totally clear on that one before we really move on to any other big homeworks and stuff, so that we at least have one clear like example of how you do an exam before we get there. Okay, so I'm saying all of that. But that said, I'm going to look at yours first, this week, before I continue going over it step by step. And if that means I have to extend a deadline on the next homework or something, I might do that. In fact, I think I did. Oh yes, I think I already, check if I'm wrong, but I believe your homework 2, which is continuation of the material. It's a continuation of the material, a continuation of what you would have been doing in lab. I believe I gave you 2 weeks to do that. Can you check Google Classroom? Is that correct? Like, I don't believe it's due next week. I believe it's due 2 Thursdays from now. Is it?
Professor, is it because for homework 2, the oscillations?
Correct. Yeah, that one. Right. So is it due? It's due
the 21st.
Great.
Yeah.
So perfect. So I actually knew what I was doing. Okay. So you'll know. So in other words, there's 2 weeks to do that. So that'll give me not only time to give you feedback on number 1, but also then that means next week we could start really going over homework 1. So I don't want you to feel overloaded or that we fall behind ourselves. So for that reason, so all that said, I'm not going to, instead of turning my attention right now to continuing to go over homework 1, I think it might be more important to start talking about the labs that you've been doing, because you've already had 2 and we haven't talked about either. So I'm going to turn it to you guys now. We're going to really hopefully make this a discussion, and it can hopefully will involve even people that aren't showing videos should still absolutely talk. I want to hear from you. Let's backtrack now. First, let's start with lab number 1. With lab number 1, first of all, did you let me just start with lab number 1. Did it feel clear while you were doing it? Did it feel clear while you wrote a report for? I mean, I assume you already had something due for it. Like, I guess I'll just start with an overarching thing. Are there any questions or concerns or things that were confusing to you, even if you think you straightened them out by now, or are confusing? I want to hear about from lab 1. Just give me anything that I can help with right now. Like, and it could be as simple as you could just tell me, I think the takeaway. Well, actually, no, let's start with that. What was the takeaway? What was the motion that you took away from lab 1? I'll ask that first. Like, what equation did you establish? And did you establish whether it was true or false?
It was the force equal the constant something. I don't remember.
Okay, but yes, I do agree it was. Okay. And let me start. whatever. So I think it was a law about the. Well, yes, it was that. Let me ask you this: whatever it was, did you establish that it was true or that it was false? Okay, I'm actually gonna turn off my board now. This might make it easier. Hold on. Wait. Wait. No, this is. Oh, I'm looking at the chat. I see the chat. Hold on. Oh, wait. Oh, hold on. There's something in the chat. Let me back up for a second. I tried to address this before, but okay, this is a direct question. I'll admit that I think okay, well, just to be clear, someone's asking in direct chat, is the homework graded based on how many questions we got correct? No, it's not. Ultimately, the homework is graded on how many steps. You get points for doing steps and you lose points for not doing steps. And even if you get all the answers incorrect, it's conceivable you could get full credit, and vice versa. Even if you get all the answers correct, but you don't put any steps, it's conceivable that you wouldn't get full credit. But on what I was saying before, right now on homework 1B, you got 25 points just for turning it in on time, and that's not your final score yet. Like it was only due today, right before class. So I have not put feedback on it or graded it for correct or incorrect or put any details. The score you got is so far. You have more points. That is not your final score. If you got a 25 on it, that just means I'm saying thank you. You got it in on time. You've already gotten 25 out of the 35 points. Now for the next 10, I'm going to look at it carefully and see if you get all the next 10 or not. And if not, you'll be able to revise it. So let me know in the direct chat person if that, and I think I put that in Google Classroom too. Let me know if that's clear now, please, in the direct chat, because it still might not be clear to everybody. But that is not a final grade. That is just a preliminary grade based on, I'm acknowledging that you turned it in. So maybe in the direct chat, you could tell me if that answered, but okay, well, but back to the lab question. Can anybody maybe even share a screen or put in the chat what motion, and you can look up, this is not a quiz, but I want to know, like look in your notes or whatever, what equation did you establish in the first, okay, great. Thank you, direct chat person. Okay, and great. Thank you, direct chat person. That's a lot of points right there. And then, and I see a hand, or maybe I see more than one. And I'm still mispronouncing. Wait, sorry, where'd it go? I just saw Takarub. And please tell me to say it correctly, your name.
Yeah, you said it right, Professor.
Oh, good. Okay, thank you. Okay, so you had your hand up. Were you going to say something? Thank you. Now you're using your voice. That's tons of points. But do you want to say something now about the lab one? Were you going to say?
Yeah, in lab 1, we just confirmed Hooke's law.
Ah, okay. Good. Okay, so you confirmed, you established Hooke's law. Great. And Hooke's law is?
The equation was spring of a force is equal to the spring constant times the stretch or compression.
Awesome. Okay. Great. Okay, that's very helpful. Thank you. And I love your avatar, by the way. Okay. Okay. A couple things I want to say about this now to get used. First of all, I agree with Takarub, very much agree. And I also agree, I think someone else had said it before and I cut her, I think it was, I forget who, but someone else, Madonna, or so anyway, someone else also said, and I agree, this is what you established in lab 1. Now, it was Hooke's law. It's Hooke's law that describes the force exerted by a spring onto some mass attached to that spring. So it's really the force of springiness or the force of elasticity. In other words, this is the force that a spring exerts on anything attached to its end. But really, in the long run, then this is the force that's exerted by anything that's made of springy material. Anything that acts like a spring or a bunch of springs, anything that's elastic works this way. And I like the way that Taco sort of put it into English, that what we're saying is that the edge, well, here, like your homework, not coincidentally, okay. So first of all, what you were establishing, what you were, I guess you could say, you did say, confirming in lab 1 was this relationship between force and displacement in the case of elastic material. Now, I want to break that down a little bit. I mean, you already did break it down in your lab. But one thing I want to establish, I asked a question that might have seemed silly or weird to you. I said, like, did you establish that the equation was true or false? And that might seem strange, but I want to make it clear right now, like in every single, and maybe Professor Moses already made this clear, but in every single lab, you're going to be given a 1 or 2 or 3 motions, like equations, statements. And your job is going to be to establish whether they're true or false. You're not always like just confirming. Like in other words, some of the equations that he'll get on some lab assignments, and it might have, in fact, I think it did already happen in lab 2, so we should get to talking about that. He'll give you statements on the board or on his very awesome PowerPoint slides that he makes, or whatever those kind of slides are. He'll give you equations, and just because he's giving them to you does not necessarily mean they're true. Your job is to set up and create an experiment to determine whether they are literally true or literally false. And either way, information will be gained and conveyed. Now, so it's like please don't think it's like obvious that you're just like going in and just like, okay, of course he's saying now we're just gonna like, in other words, there's a question that has to be answered, which is this thing true or false? We don't know until we do the experiment. So if your data really shows that something is not right, that doesn't necessarily mean you did the experiment wrong, or you should just say, oh, okay, but it's not the ideal world, so blah. No, like your job is to find out whether they are true or they are false. And very often, many of the statements will be false. Now, this one was true. This first starting statement of the year is F equals negative kx. Yes, it's true. What it means to me is what I have on the screen right here. Like what it means to me is from now on, if I put an object at the end of a spring, there's an equilibrium position associated with that spring. I think we said this last time. Like the spring, the edge of the spring, if one end of it is attached to a wall, I should say that too. If one end of the spring is attached to a rigid object such as a wall, and the other end of the spring is attached to some mass, some particle that I'm going to measure and study, the edge of the spring will be in a certain spot. If I don't do anything to it, it'll be comfortably resting at a certain spot that we call equilibrium, a certain position, and we designate as x equals 0. And if we pull the mass away from equilibrium, as you thought about in homework 1 and as you studied in lab 1, if you bring, and I don't care whether the thing is horizontal or vertical, the truth is horizontal springs are easier to theoretically analyze, but vertical springs are easier to experimentally analyze, and it comes to the same thing. So anyway, if I pull a mass away from the equilibrium edge, then the whole idea of elasticity is the spring will exert a force on that object which attempts to bring the object back to equilibrium. The force will always have a negative sign in it, because if I pull the mass to the right, the spring force, if I displace the mass to the right of the equilibrium position, then the spring will exert a force attempting to restore it to equilibrium. So the direction of the force will be to the left, hence this negative sign. And if I were to squeeze the spring, if I were to compress the spring and put the mass on the other side, on the left side of 0, on the negative side of 0, then the force will be pulling to the right. So it's always the opposite of whichever way the mass is displaced from equilibrium. So the force exerted by the elastic material is always in the opposite direction from displacement. We call that fact alone, we call that negative sign, that fact, restoring. And then the key of this, I'm just summarizing what I think hopefully you already established in lab 1. The key is that the force is not a constant force. This is the main thing to take away from this, from all this. In some respects, this is like how, in some respect, if I have a mass above the ground at a certain height, then there's a force called the gravitational force, which tries, or the weight of the object tries to bring the object down to the equilibrium position of the ground. I mean, in that sense, there's a relationship between spring forces and gravitational forces, but a big difference that we're trying to establish right here, right now, is that the weight of an object, mg, or negative mg, if you like, the mg of an object that tries to bring it to the ground is a constant force. I don't care how high I hold some m. I could hold it at 1 meter or 3 meters. The force trying to bring it to the ground is still just its mass times 9.8 meters per second squared, mg, right? It's a constant force, irrespective, independent of displacement from equilibrium. The spring force, the key of the spring force is it's the first force we look at in physics where the magnitude of the force is actually proportional to or related to, dependent on, a function of the displacement from equilibrium. The force grows and grows as the displacement from equilibrium grows, right? That's like the interesting news. The good news is that it grows in a straight line way. It grows in as simple as possible way, a direct proportionality, linearity, if you like. And so if we were to make a graph of how much force, extra newtons, the spring is exerting on that mass for every extra meter of displacement that the mass is held from equilibrium, if we were to make a graph of how many extra newtons of force are exerted for every extra meter of displacement we experience, we would find not a horizontal line, but a straight line, a diagonal line. It would be in the fourth quadrant, as my graph is here, because it's all negative. It's all in the opposite direction. You know, if the force is if the displacement is positive, then the force is negative, and vice versa. So it's in a weird quadrant. But the point is, it's a straight line. It's which is very nice. And that means it's a function whose slope is a constant. What is the slope? The rise per run, right? So you could say the change in y per the change in x, only in this case, we're not graphing y versus x, we're graphing f versus x, newtons per meter. So the slope of this graph, the slope of the force displacement graph, is what we ultimately call K, this constant number that does not change. It can change from one spring to the next, but it doesn't change within one spring. No matter what you do to the spring, it has a certain K, a certain amount of strength that it exerts for every meter of displacement. That strength is measured in newtons per meter, right? Because it's rise per run of this graph. It's measured in newtons per meter, and it ultimately is called the stiffness of the spring, right? So the stiffness of the spring is the constant of proportionality between the displacement that you ask it to undergo and the force that it responds with. That's a summary of what supposedly we took away in lab 1. I'm just looking at the time again. Okay, now obviously you have to do more and all this, but that was like, that's the nature of elasticity. Gravity works as a constant force. Gravity is a certain kind of force that works in a certain way, a constant way. Elasticity the nature of elasticity is that it is a force that is not constant. It is dependent on displacement. Well, here, okay, so takeaway. Okay, the takeaway is that the elastic force, it's not constant. It's not a horizontal line. It's one step more complicated than that, which is why we have to look at it carefully. But luckily, it's exactly one step more complicated than that. The elastic force is not a constant force, but it is a linear force. So it's like as nice as it could be. It's as manageable and studyable as it could be for something that does change. That's sort of the takeaway from lab 1. Luckily, we still have time. I mean, well, luckily for me, we still have time. We're trying to get ourselves all caught up and ramped up here. So let me just pause for a second. Were there any? Well, let me ask you this: Did you already turn in something from lab 1, or did you ask for something yet for lab 1, or is it still due?
Both lab 1 and lab 2.
Have already been. They're both already due. You're saying?
Yes.
Yes.
Okay. Thank you for. And by the way, I don't know who that
Graded.
was. Sorry, that was Sadie. Okay. Thank
No,
you.
it was
Okay. Oh, sorry. What? No, you. What?
no, I was saying, yes, it was already due, and one of them was graded, which is, believe, with the first one.
Oh, and sorry, and that's Madonna, not Sadie. Okay, I see now. Oh, okay. So you already got back lab 1. Okay, so I know. Okay, great. Thank you. So we should move to lab 2, but just quickly, because we haven't. Again, the two parts of this course are really supposed to communicate with each other. It is all supposed to be related. So, and so that you know, also, he and I talk every week. I mean, this is not. It's all. it's all together. And of course, he's the authority over everything that happens in the lab and in the grades and all that. And then ultimately, if there's ever, quark forbid, electron forbid, if there was ever like really an issue between anyone, you always bring your issues to him first if there's something in lab. But then if it's a really gets something, then of course you come to me or he'll come to me or whatever. But what I want to ask right now, since you already got back lab 1, that's great. I'm pleased. Is there anything to any of you that is unclear still from lab 1 that you'd like me to help try to resolve right now before we move on to because that is partly what I'm here for. Obviously, if you can't read his handwriting or he took off 2 points here or something, okay, go to him. But is there any concept or any expectation or anything that is unclear that anybody wants to probe from lab 1 before I move? And I mean that honestly. I'm looking. I'll look in the chat. I'll look in both places of the chat if I can figure out how. Hold on. I just want to make sure. Why do I never know how to do this? Where's Gus Johnson? Oh, maybe there is something in the chat. Okay. Wait, I'm looking. Oh, well, Alexander, I was saying before, sorry, Alex, I don't think we will. I was saying that before. I think that next week we go over homework 1B. I will try, but you have 2 weeks to do the next homework. So I want to grade it first and see what I need to tell you all about and what I don't. But if anything went really wrong with it, once I go over it, you'll still have time to redo it. But I do apologize. I think today, maybe we will if it keeps going like this. But my plan first, I wanted to catch up with your lab materials because that's been disjointed. So I was saying before, I apologize. I'm not promising that we will go over homework 1B today, but it's the first priority for next week. That I do promise. And if I did it, you see, okay, thank you. Okay, sorry. Okay, but very fair question. It's certainly a fair question. Okay, we turned in lab 1. Okay, let me look at the other chat. There's 2 different chats going on. Hang on one. But if there's no other questions about lab 1, I might do backsies on what I just said to Alex, because if there's no issues, there's no issues. Then we can. But hold on, I'm looking if there's another chat. You might have said something. Yeah, there is another chat. Okay, hold on. There's 2 chats. Oh, no, okay, that's it for the chats. Okay, so let me ask now. Maybe I'm opening a can of worms here. But in my experience, lab 2 is harder than lab 1. Lab 2 does leave more room for confusion. Now, I don't want to create confusion if there isn't any there. And frankly, I also think Professor Moses is like one of the clearer people I've met in a while. Like, I'm really pleased. I hope you are. And if not, give it time. I think I think he hopefully is much more clear and concise than I am. So maybe there's no issues. But if with lab 2, I'll say this. Lab 2, if you've done it, but you haven't turned it in yet, is there anything that anybody wants to ask me right now that maybe I can help you right now with anything that you have to write up for him? If there's, we'll just leave it at that. Like, if you think you're solid with it, great. I'll move on to homework 1B. But maybe right now, let me give you an opportunity first. If there's any question that anybody has about what's expected or what they were trying to find out or how they're supposed to write up anything for lab 2, this is a good time to ask. And I'll pause for a second to. So again, I'm saying, so I won't walk you through lab 2. I'm looking at the chat. Oh, yes, that's fair. It is. I agree. Yes, it is. Fair enough. And I'm not saying it was fun. I'm just looking at the chat where Taco Group said it's maddening to try to count the bounces of the spring. But I would also take it to mean, does that mean you somehow eventually prevailed and you eventually, but yes, I sympathize. I think that's true. Do you guys know what's expected though? Do you want to even check with, do you know, did he tell you at the end which motions were right and which were wrong? Or do you feel confident about that? If you do, again, I don't need to make anything problematic. If you think you guys are set to write the reports, and I'm not being sarcastic, I'm happy to go to homework 1B, but I do think it's part of the opportunity and the responsibility of this course that if I can help you before next Tuesday. So okay, I'm going to ask directly. You guys think you're set to write whatever it is he wants you to write up for homework for lab 2? Oh, okay. Thank you, Caitlin. That's helpful. Okay, maybe he didn't. So Do you want to check with me? Do you want to run? Does anybody want to run by me what you think is correct and incorrect? And I'll just tell you right now. I mean, I think that's fair. That's not cheating. Do you want to check with me?
Yes, absolutely. I think my table had a lot of difficulty.
Oh, okay. No, that's fair. And that's what we're here to find out, especially at the beginning of the semester. No, that's fair. So, okay. Wait, and I don't even know who was, I think I know who's, so now what I can't do is just off the, so how about, if you give me one of the specific motions that if you could tell me one of the motions that you were having trouble with, I will tell you whether it's right. I mean, I might talk a little bit, but I'm not going to just pull out of the air stuff. So if you tell me one of the motions that you were struggling with, I will tell you what I think the deal is.
I think the one that we had trouble with was T alpha m squared. The fourth, no, that's one. I think that's 2 or 3.
That is definitely one of, okay, now you're talking now. And again, I kind of need you to, okay, good. So wait a minute. And thank you, Auntie. That's Auntie. Yes, that's it. Okay, good. And she's using her voice and all that. So, and it might help. I'm going to write this down. I think this is more, again, honestly, we can't do everything in one class. I'm feeling a little bit apologetic to, like, I think it was Takaru and other people. Remember, again, if we don't get to homework 1B today, that's okay, because you have 2 weeks to do the next one. But I think if I can help you now write up whatever's, I think this will be more directly, fastly helpful for you for the next lab class. So what I'm going to do is, first of all, what Antigone just said, I'm going to write down. But if anybody else, whether you had difficulties or not, if anybody else in the chat or somewhere can just tell me what they think the other motions are, whether they're true or false, it might also help me feel more confident that you all are like, that we're all on the same page. One of the motions is definitely what Antigone just said. And I don't care what the order is. The order doesn't matter. But one of the, there were a bunch of motions, like about 4 of them, yes. And one of them was, so I'm going out of order, doesn't matter the order, was something that looked like this, I believe. That's what Antigone's talking about? Yeah. Or can you see? Oh, you can't see the screen anymore. Can you see the screen?
No, we can't see the screen.
Oh, you can. Okay. So am I correct? Okay, thank you. Awesome. Am I correct, Antigone, that that's one of the ones you're talking about? Or that is the one?
Yes. It was also, I'm not sure if you want all 4 of them.
Oh, sure, please. Yes, sure. Okay.
That one, and then T alpha square root of M, or M square rooted.
Right. Which do you agree I could also write it like that? That's the same. Or in other words, people might not know this, but these two are the 2 ways of writing the same thing. Is that fair? Okay. And yeah, you might as well complete the whole list. Sure, complete the whole list if you don't mind. Okay.
The first one was T alpha M.
Right. Good. Okay.
And then the fourth was T alpha X to the sub-0. Like 0, the little, yeah.
Right. And just like that, no power, no exponent. Okay. Very good. Okay. I will, if nothing else, to make your life worthwhile, I will promise you this by the time of this class. If nothing else, I will tell you the answers. I will. Because of course, you still have to explain everything and blah, blah, blah. Like that will be cheating, but I can at least, I will. Let me back up for a second though. And I'll probably go in this order just because this is the order we said. But let me, first of all, that alpha, that may be throwing some of you up. I want to quickly say, when we write, let me first say, really important notation in physics. First of all, I don't remember if I said this last time or not, but if I ever use a triple equal sign, that means equal by definition. That's very important. It's I don't know if I said that last time or not, but triple equal signs are not the same thing as double equal signs. Double equal sign, you could write this down. If I never said it yet, I'm just going to say it. I'll say it a lot later. But double equal sign means equal by discovery or circumstance or condition. Triple equal sign means equal by definition. Very important distinction in physics. I'll say it one more time. Double equal sign means equal by circumstance, discovery, or condition. Triple equal sign means equal by definition. Really important to keep that straight. For like we make discoveries in the lab of double equal signs, but triple equal signs are like in physics 101 when you say average velocity equals displacement over time, and you think of that as an equation, and some of you think of it as a formula or whatever. What that is a definition, right? Average velocity triple equal sign displacement over time. And it's so important to know that because the fact that we never ever discovered that in a lab, therefore we can never undiscover it in a lab. If average velocity ever equals displacement over time, then it always equals displacement over time. In other words, triple equal signs are more reliable than double equal sign. Whenever we know something's a triple equal sign, we know it came from a dictionary. It didn't come from a experiment with error and uncertainty and all of that. Okay, so anyway, that's a sidebar. But if I ever use a triple equal sign, I'm saying defined to be. Now, that alpha symbol, that's some of you are comfortable with, but I know from experience that some people are not comfortable with this alpha, even like after many uses of it. The alpha means directly proportional to. Now, we're all about direct proportionality right now. We're trying to figure out, in every single lab in this whole course, we're trying to figure out how two quantities are related. Honestly, that's what you always do in every single physics lab. You're trying to tweak one knob called an independent variable, and you're trying to find out how Mother Nature responds to your knob tweaking, how she, in response, tweaks some other knob. You play with an independent variable, and you hold everything else constant, and you watch to see how Mother Nature responds in the dependent variable. Always what we're trying to find is a relationship between two variables. Physics felt last semester like you plug into formulas, maybe, or maybe it felt that way in high school. The truth is when you do physics, as we're hopefully doing here, we're not plugging into equations. We're trying to develop the equations from the lab. So we're trying to figure out how one thing is related to another. Sometimes things are related in a directly proportional way. When they are, we're very excited because it's the easiest relationship to deal with. It's not always the case, but we always like it when it turns out to be. When y is directly proportional to x, what that literally means, it doesn't mean y equals x. It means y equals x times some constant. Like literally, that alpha is a stand-in for equals m or times x, or equals a times x, equals some number. I don't care whether you call it m, we tend to call it m in math classes, or if you call it a, or you call it the number 7 or whatever. The point is, when we use that alpha symbol, we're saying we don't know what the constant is. We don't know what the constant is, so we can't set this thing equal yet. But we know if y is directly proportional to x, it means that if we were to make a graph of y and x, it would be a straight line. We don't know what the slope is, so we don't have an equation yet. That's why we use the alpha. Alpha means, if we say y, alpha x, we mean y equals some slope that never changes times x. And probably our next job is to figure out the slope. But okay, so that's what the symbol means, just saying. Now, back to Antigone's actual question. In terms of these motions, what we're really trying to figure out in each of these motions, what we're trying to get at is, you've got, I'm just looking at the time. Okay. You've got this mass that's going back and forth on the spring. You're counting. What you're ultimately trying to figure out, as I think you know, you are trying to figure out the period of oscillation, the amount of time that it takes this mass to do one full cycle. So what you did was, as you know, you set the mass in motion, you let it go for a number of cycles. you had the difficult time of counting those cycles, and you probably didn't, and you probably counted a number of cycles in, say, 20 seconds or 10 seconds or something like that. And say you did it in 10 seconds. So you saw how, sorry, I'm saying this backwards. You took the amount of time it took for the thing to do, say, 10 cycles, let's say. And whatever amount of time it took to take 10 cycles, you then divided by 10. So now you had some kind of average or some sort of approximation, some imperfect but experimentally derived result for what the period of oscillation for this mass was. What your ultimate goal in the lab was to find out what's the determining factor, or what are the determining factors behind this period of oscillation. What independent variables, so I'm just gonna write this in. Hold on. So first of all, just to summarize, and I promise I will answer Antigone's question. I mean, it's like the perfect question. I'm just trying to give a full answer. And it probably will be the last thing we do in this class is get an answer to Antigone's question. But so just backtracking for a second, like what you were trying to do, if this context was lost, you were like looking at a spring, and what we were treating t, you notice in every one of these example functions, t is treated as the dependent variable, t, capital T, which stands, capital T, which stands for period of oscillation, amount of time for one cycle of an oscillating mass on a spring. You are treating that period as the dependent variable, as the output. Like T is what you would put on the y-axis of every one of any graphs that you try to make, right? T is the output, the dependent variable. And what you're trying to do with playing around with these different functions, you're trying to see what is the independent variable? Like what is it that when we tweak, it affects that period? So you're testing different independent variables like mass and initial displacement. But then more than that, more specifically, because you're really only testing two, I suppose, then more specifically, how? You're asking, how does the independent variable drive the dependent variable of period, right? You're ultimately trying to figure out in other words, you are trying to figure out what does the function look like, which is ultimately all we're ever trying to figure out in physics. What's the function that describes how one variable relates to another? Again, it might feel like physics is all about plugging into functions, but actually physics is about developing functions. What does the function look like? And so now I'm almost at Antigone's. Okay, we still have time. So we gave you, instead of like, so, and this is the way that these labs will always be, we're not just putting you, we're asking you to design your own experiment. We're giving you a lot of like freedom, or like a lack of a certain recipe, which stresses some people out, I know. But we're giving you a focus, and we're saying like, all right, here's some examples of what the functions might look like. We're not just asking you to come up with the function out of nowhere. Here's examples of what the functions might look like. Can you test and see if the relationship does resemble any of these? And of course, you do that by getting a bunch of data and then putting it on graphs and seeing what your graphs are doing. Now, one thing, so I'm going back now to The reason we phrased all of these as direct proportionalities, this is a big sort of hint or lesson in experimental physics. A function could be a straight line function, or it could be a parabolic function, right? It could be like a y equals mx plus b, or it could be like a y equals ax squared, right? A parabola, right? Or it could be like a cubic, y equals ax cubed. They could get more and more complicated, or they could be some other kind of thing like y equals sine of x, cosine of x. Like there's all these different functions, relationships between two variables that you know about in theory in math. Now we're trying to use them to describe patterns in nature. The thing is, all of us, not just students, all of us, physicists, always like the linear functions the best. The linear functions are the easiest to deal with. So the first thing we always look at in any bunch of data that we get, we always first look to see, is there any way we can arrange this data, analyze this data so that it falls in a straight line? Because we can tell when something's in a straight line, and we can get a slope easily and all that stuff. So each one of these questions, and I will answer, but I want to start by saying these different options, especially like 1, 2, and 3, what 1, 2, and 3 are all saying, they all suggest that t is a function of m. They're all implying the possibility that if you tweak the mass amount on the end of your spring, like if they're all suggesting that if you were to try different masses on the spring, you'd get different period values. So presumably you did that. Hopefully you did that. Of course, none of your data is perfect. We all know that. But like, hopefully you tried a certain mass and you took like 3 trials or something and counted up the amount of seconds it took to do like 10 oscillations and then divided by 10. So you got like, for a given mass, you maybe got like 3 different values of t and then average them together to sort of reduce error. So then for a given mass, you got a value of t. And stop me if this is crazy, but this is what I'm envisioning. And you put it in a table of values. Then you try a different mass, right? If you're trying out any of these first 3 functions, you'd be trying different masses, seeing what period they produce, maybe trying each different mass like 3 times, averaging them together just to reduce error. But eventually you have, let's say you tried like maybe 5 different masses, or even 4. I mean, the more the better, of course. And each one of the masses that you tried, after you took a couple of trials and averaged them, each one of those masses has a corresponding period. So each one of them would be a point on a scatter plot. Like, I'm talking fast now, I know. But hopefully, for any one of these that you were trying, especially let's say number 3, right? Number 3, literally you would do literally what I just said. You would try different mass values, see the corresponding periods that they produced, make a scatter plot out of it, right? Like literally, you know, whether it's on Excel or Desmos, ideally, hopefully, eventually Desmos is better. We'll talk about that. But wherever you made a scatter plot, and if, so now really getting almost, it's gonna be 5 minutes, I'm almost at Antigone's answer. If you literally tried different masses and plotted the different t's and made a scatter plot, if your dots, if your dots basically made a straight line, including the point 0, 0, because I'm going to sidebar this, it's always important. 0, 0 is sometimes a point on graphs, sometimes not. But always you can ask yourself in your mind whether you think it should be. Like if you put 0 mass on this, do you think it would take any time for the spring to go back and forth? I think you could see in your mind it would not take any time for the mass to go back and forth. I think in your mind you can see that 0, 0 for a situation like this would be a point. If you believe it would be a point at all, it's your most reliable point, right? Because it's the extreme limiting case. So put it in. If you don't think it makes sense, don't put it in. But if it makes sense, put it in. What I'm trying to say a little bit quickly now is, if the points on a t versus m graph created a straight line, then number 3 would be true. But I'm going to tell you right now, to address Antigone's, with 4 minutes left, I think if you are following what I'm saying and you did something like what I'm saying, I think you would find that number 3 is not true. T is not proportional to M. You don't get a straight line. You get some kind of curve. When if you like, and it doesn't maintain a constant slope. It gets less and less steep, I believe. It starts at 0, comes 0, and it goes like that. It goes like that or something. So then the question, now it is a dependence. It's not a horizontal line. So it clearly shows that period does depend on mass, but not in this direct way. Not in this simple way. The question is, what aspect of mass does it depend on? Does it maybe depend on the mass squared? Does it maybe depend on the mass square rooted? Well, the truth is, if you just look at that curve if you look at the way your dots are, if you recognize that curve from a math class right away, you might have a conjecture for this, maybe. But the key point, and I know we have 2 minutes left, and you might already know the answer just from but if you don't, the key trick of physics is you don't have to already know the answer. As long as you know this thing is not a straight line, the trick for Antigone's question and for everybody, for proposition 1, or motion number 1 and motion number 2, is the way to test those. I'm going to say, you might have to replay this recording. This is possibly the most concrete, important thing I'm saying in 2.5 hours. The way, because we're going to do this a lot, the way to actually test motion number 1 or motion number 2 is, what you do is you take all your mass values that you got, right? And you don't have to take any more data. You just take your data that you already have. You take each mass that you used and you square it. And you put that on your x-axis, but you don't change the period. Like if originally you had a mass of 200 and it mapped to a period of 5 seconds, then what you do is you create a new graph where instead of the point 200, 5, you square the 200. You make it 4,000, 40,000, and you map that with a period of 5. Like you square all your m's and correspond them to the original t's, and you make that graph. If that graph is a straight line, then that will show that t is directly proportional, not to m, but to m squared. Do you see you may have to replay that, but I'm saying the way you test the first one is you just square all your m values and map them to the original corresponding t values. I will tell you right now, if you do what I'm saying, you will get that first one is false. It doesn't work. Why? Because the real answer, if you look at my picture, if you look at the way your data fell for t and m, you'll see that it doesn't go in an upward concave up parabola. It goes in a sideways parabola. It goes into like x equals y squared, not y equals x squared. X equals y. I'm talking very fast, I know. But I'm just telling you the answer so to help you, so you at least know if you're doing it right or wrong. I'm telling you that data, if you did it vaguely correctly, actually falls in a pattern like that. Like, I don't know what order you had the motions in, but the actual correct answer is that t turns out to be proportional to the square root of the m's. In other words, every one of your m values, if you, from your table of values of m and t, take every one of your m values, square root it, and map it to whatever t was sitting there in that same row originally. Make a graph out of those, and you'll see, if your data is fairly good, you'll see that you get a straight line. You don't get a straight line when you map t to m, but you get a straight line when you map t to the square root of m, because as it turns out t is proportional not to m, but to the square root of m. And that's actually the correct answer. Also, just so you know, the last one's false for a completely different reason. The last one, you should get a horizontal line, basically horizontal line. It doesn't matter where you start the mass. It should have roughly the same period no matter what.
So excuse me,
that was very
Professor?
fast, I know. And I think class is over, but I'm going to hang out for any questions. I know you guys have to go. Hopefully that helped a little. Hopefully I'll post this recording. Maybe if Antigone could stay for a second and just let me know if I answered the question, that'd be good. But either way, I'm here until the last person leaves for any questions or whatever. We'll pick up with homework 1B next time. You don't have anything new due next time. You've been very patient and very good. I'll have my computer back next time, hopefully. So thank you all very much. But I'm here for any questions that anybody might have. And I'll stop the recording.
Professor, just to clarify, it's t is proportional to m square root of m. That is the truth.
Yeah, that's what I'm saying. Yes, that's true. Yes. Oh, cool.
Thank you.
Okay, and that's the only one. Yeah, that's right. It makes some sense. Okay.
It makes perfect sense. Thank you so much.
Okay.
Professor.
Okay.
Thank you,
All right,
Professor.
guys so
Professor.
much. Okay.
Have a good
Bye.
day,
Thank you
Professor.
guys so much. Bye. Bye, guys. Bye, Josh. Bye, Madonna. Bye,
Bye.
Tanya. Bye. Bye.
Professor.
Oh, yes. I'm still here. Yes,
Professor.
I'm sorry. Yes. Let
Yeah,
me try to
yeah.
stop
So just to
recording. Hold on.
yeah,
Oh, thank you. Wait, hang on one second, just so I don't record you accident. Hold on one second. Or if I can't, I can't, but hold on one sec. If I can, oh, stop. Okay, okay.